We're going to look at an additional example of problems involving setting up equations using the Pythagorean Theorem. So we've got this situation here. An isosceles triangle has a perimeter of 50. The altitude is 5. I want to find the individual side lengths. All right. So I'm going to make a sketch here. I don't know exactly what this is going to look like, but maybe something kind of like this. The perimeter is 50. The altitude is 5. All right, so I'm going to put an altitude in here. The perimeter is 50, and it doesn't tell me anything about the individual side lengths. So I need to incorporate a variable here somehow. I really need to try to keep this to one variable. Okay? So for example, if it's an isosceles triangle, I know that those two sides are equal. Maybe I can make the two equal sides x. Okay? I could make the base x, but I think it would be a little bit simpler if I make the two sides x. So I'm going to do something like that. Okay? And here's the key. I need to try to describe the third side of the triangle using those same variables. And here's why. What I'm really trying to do here, the altitude is going to hit the base of this triangle at a right angle. Okay? We know from proofs earlier in the year that you can prove that these two triangles would be congruent right triangles. Okay? So what I'm really trying to do here is I'm trying to get all three sides of one of the right triangles labeled. And if I can get them all labeled using numbers and the same variable, then I should be able to write a single variable equation by substituting everything into the Pythagorean theorem. That's the big idea, all right? So here's my thought. The perimeter is 50, right? I need to write an expression for this side, okay? All three sides add up to equal 50, which means if I subtract these two sides from 50, that should give me a way to represent the third side. So in other words, I'm going to take my perimeter of 50, I'm going to subtract these two x's, okay? That expression gives me a way to represent the third side. And by the way, you can check this. Remember, if the perimeter is 50, the three sides have to add up to be 50, right? So if I take 50 minus 2x, and I add x, and I add another x, that's going to cancel those two x's, and the three sides add up to 50, okay? So it works even when I try it, okay? This side's bisect. So I can take half of this, 25 minus x, and put it here. And take the other half, 25 minus x, and put it there. And now I've got everything labeled. Specifically, I have the sides of a right triangle labeled. Does everybody see this triangle right here? That's really the triangle I'm looking at. Okay? That's a right triangle. I should be able to use the Pythagorean theorem here. Okay? So what's that going to look like? Well, the Pythagorean theorem says that a leg squared plus a leg squared is equal to the hypotenuse squared. Okay? So a leg squared, 5 squared, plus a leg squared, 25 minus x squared, is going to be equal to the hypotenuse squared. The hypotenuse squared is going to be x squared. All right? Now, this is going to take some simplifying. We're going to have to do some work here. That's going to be 25. 25 minus x squared, that's 25 minus x times 25 minus x. Remember, you cannot just square these two values. There are no exponent rules for addition and subtraction. Think back to that idea from Algebra 1, all right? So 25 times 25, you might know it, you might not, ends up being 625. Minus 25x, minus 25x. Be careful, negative times negative is a positive x squared, okay? So we're going to get 625 minus 50x plus x squared, okay? So this whole thing is going to simplify to be 625 minus 50x plus x squared, okay? This is the whole left-hand side of the equation, and then it's equal to the right-hand side of the equation, which is x squared, okay? Now this simplifies a little bit. That's going to be 650 minus 50x plus x squared is equal to x squared. And here's a really cool aspect of this particular problem. Notice that I have an x squared on the left, and I have an x squared on the right. I can subtract x squared from both sides. The x squareds are going to cancel, and that means I no longer have a quadratic. These guys are gone. I've got 650 minus 50x is equal to 0. Okay, I can add 50x to both sides. I get 650 is equal to 50x. You just have to figure out how many times 50 goes into 650. Okay, and I believe x is going to equal 13. Okay, so if we go back to our original diagram over here, x is 13. We can fill that in. This x is also 13. Okay, each of these sides is going to be 25 minus x. So 25 minus 13 is 12. 25 minus 13 is 12. And so the side lengths of my isosceles triangle end up being 13, 13, and 24. That ends up solving the problem. All right, for the following problem, I have a triangle with side lengths of 13, 14, and 15. And I want to find the length of the altitude of this triangle, okay? And something we have to keep in mind here, this triangle is not necessarily a right triangle, okay? This looks a little bit like a right angle, but if you notice, this is actually the longest side. If there was going to be a right angle, it would be right here. There's nothing particularly in the problem that suggests that the original triangle is a right triangle, all right? Now, the idea that I've been pushing in the previous problems I've posted has been that if you possibly can, you want to try to label all three sides of a right triangle using the same variables, right? This is going to be a little bit different. If you notice, I can put an altitude in here. This is a right triangle. That's a right triangle. I don't think I have enough. I don't think there's any way that I can label all of those sides using the same variables very easily. So I'm actually going to adjust this just a little bit, and it's going to be based on one fact. Notice that I now have two right triangles. When I draw that altitude in there, I've got a right angle here, I've got a right angle over here. As a result, because I have two right triangles, and they're different right triangles, I should be able to write a Pythagorean Theorem equation for both of these. And if I can write two equations, I could have two variables, and I could write and solve a system of equations. All right? So a little bit different strategy than what we've had previously. If you just have one right triangle, I would try to label all the sides using the same variable, set up a Pythagorean theorem with those variables, and you'll be done. But if you have two different right triangles, you may be able to put an extra variable in, and you may be able to get things to work out a little bit better. So I'm going to label this side x. Okay? This whole side here is 14. So if I take away x from 14, I can label that side as 14 minus x. Okay, so we can do that with that one variable. But I don't know anything about this side length in relationship to these sides. Okay, so I'm going to put a second variable in there. I'm going to call that a y. And again, the only reason I can do two variables is because I have two different right triangles and can do two different Pythagorean theorem equations. Okay, so check this out. I know that x squared plus y squared is going to be equal to 13 squared. So there's one Pythagorean theorem. Okay? I know for this right triangle over here, this leg squared plus this leg squared is going to be equal to the hypotenuse squared. So 14 minus x quantity squared plus the hypotenuse squared is going to be equal to, I'm sorry, the leg squared plus the leg squared is going to be equal to the hypotenuse squared. And by the way, I forgot to square the hypotenuse there, so let's do that as well. All right, so that's what I've got. This needs to be FOILed out, okay? That's 14 minus x times 14 minus x. 14 times 14 is 196. You have minus 14x, you're going to have another minus 14x, you're going to have a plus x squared. Okay, so this is going to be 196 minus 28x plus x squared. That's what this statement right here is going to work out to be. Okay, so we can solve systems a couple of different ways. I've really pushed the idea of using elimination, adding two equations together, trying to get one of the variables to cancel. This time I'm going to do something a little bit different. I've noticed here, this is in terms of x. If I could solve for y squared, I could get one equation with one variable, and it would be relatively easy to solve. So I know that x squared plus y squared is 169. If I simplify that, x squared plus y squared is equal to 169. I can subtract x squared from both sides, and I can find out that y squared is the same thing as 169 minus x squared. Okay? And I could put that in place of y squared in the second equation here. By the way, the hypotenuse should be squared there in both of those. And then I can have one equation with just an x variable, and then I can get a solution. So this is really going to be a solution method using substitution. So this is 196 minus 28x plus x squared. Okay? Y squared is the same thing as 169 minus x squared. So in place of y squared, I'm going to put 169 minus x squared. Whole thing is going to be equal to 225. Okay? And you should be able to solve an equation. One of the things that's really, really nice here, notice you have a positive x squared and you have a negative x squared. The x squareds are going to cancel. This is not going to be a quadratic in the end because of the substitution process. So I need to simplify this. This is going to end up being 365 minus 28x is equal to 225. If you add 28 to both sides, 28x to both sides, and you subtract 225 from both sides, you're going to get 140 is equal to 28x. X is going to end up equaling 5. Okay? Once you have x, you can put x back into one of your equations, and you can find y. 5 squared plus y squared is going to be equal to 13 squared. You've got 169 minus 25. Y is going to end up equaling 12 when you go through the whole process, okay? And so what you're going to end up having here, x is 5, so 14 minus 5 is 9. Y is 12, and x over here is 5, okay? So we end up having side length of 14, side length of 13, side length of 12. The altitude of the triangle ends up being 12 units, okay? So this is kind of a last-ditch effort that I normally make. But that's if I have two different right triangles. You can use two variables. You can write two Pythagorean Theorem equations, and you should be able to get a system of equations that you can solve using substitution, which will enable you to find a solution.